With the scenarios elaborated, you see, particularly in scenario 3, the only solution or the only effective solution to a congestion is to what? Just slow down. And therefore, the two key design elements in a congestion control mechanisms are these. First, detecting when a congestion is occurring. Second, notifying the traffic sources that's causing the congestion to slow down. And there are two major approaches allowing us to achieve those. First is called the end-to-end based approach. The other, the network-assisted approach. Now, from the name of it, you probably guessed. Yeah, end-to-end meant the end systems are doing much of the work, detecting congestion, informing the traffic source to slow down. Network-assisted, on the other hand, is asking the routers to do all these work instead. Let's first focus on the end-to-end approach. So in this approach, the end systems will need to infer if there is a congestion occurring inside the network. If you recall back in TCP, okay, what we're doing is sending multiple packets in one flight to the receiver. Receiver is sending ACK back. And all these packets and ACKs carry the sequence numbers. So receiver can actually detect a gap, okay, in the packets being received, and therefore sends duplicate ACKs instead of new ACKs. So receiving duplicate ACKs is a way of detecting if there's a loss, or the sender side can simply time out and then retransmit. That's also a signal of detecting there's potentially a congestion inside the network. So that is, observing from the loss occurring, inferring there's a congestion. One can also observe if there's delay changes. Okay, so for example, when we send packet out, let's track the sending time. Okay, let's track also the time when the ACK for the packet comes back. Calculate the difference, you get the round trip time. And if you observe for a long enough time, you might see, oh, the round trip time is increasing. When it goes beyond a certain threshold, then you could say that, also, network is running into a slight congestion there. Okay, so overall, general mechanisms, observe packet losses. If there is an increasing trend, observe the delay. If there is an increasing trend, then you're going into this hotter zone where congestion is likely occurring. Now, taking this approach, we do not get explicit feedback from the internet, from the routers inside the internet. And taking the end-to-end approach, we'll have to also guess or infer the right sending rate. Okay, so this is for the source to know exactly what is the right rate to send the data so that we do not overwhelm the network, in the meantime not being too conservative, too slow sending the data out. Okay. And this is actually rather hard to do for the end systems. After all, they are actually at the very edge of the network. Congestion could be happening anywhere inside the network along the path. Okay. So what the end-to-end approach is doing is this, okay, guessing. By trying a certain rate and observe if there's a loss, okay, if there's a growing delay. If not, then cool. This is actually within the available bandwidth. So maybe let's raise the rate a little bit and see, right, if there's a loss now, if the delay increases now. If not, then hey, we're still safe. Let's, increase it so that we're not too conservative, too slow sending the data out. Now, but if we exceed a certain point, and as a result, we begin to see loss, and we begin to see the delay increasing drastically. Yeah, that is actually not good. That indicates that we are probably exceeding the available bandwidth threshold, and therefore we are sending data too much, too fast into the network. So if we are failing, if we are detecting the signals of congestions, then that's slow down. Okay, so end system here to infer, to find out what is the right sending rate is by trying. Okay, pushing. If we over push it, let's come down again and then try to push it again. Well, if not good enough, slow down again. So this is in fact the approach also taken by TCP. This is actually very natural because TCP being a transport layer protocol, it's actually implemented receiving side, sending side both at the end systems. Therefore, it implements an end-to-end based congestion control mechanism. The network-assisted approach. Okay, so in this approach, routers will be doing the congestion detection. But how? Well, we also need to observe something, but this time we could actually observe something that's very directly related to congestion. This, the queue size. Okay, so this is the queue of these packets gathering at the entry point of a router. Okay, so congestion is this: sources of the traffic sending data too much, too fast into the network. Inside the network, we have these routers, right, handling packet forwarding. If the outgoing rate is slow and incoming rate is high, then these packets will need to what? Be buffered temporarily, okay, at the entry point of these routers. And therefore, they get a chance to wait for their turn to go out on the outgoing link. If the outgoing rate is slow, incoming rate is high, queue gets long, and free buffer space gets small, right? So queue size or free buffer space, okay, changes of these, okay, are good indications of a congestion occurring. Now, routers, however, are the devices in the middle, okay? How do the routers inform the sources so that the sources know that they need to serve them? Yeah, this is the way it's done, okay? So there are these bits, special bits, okay, inside the packets. So when these packets travel through a router, and the router is so busy, queue size is so big, or free buffer space is so small, these bits get turned on. Okay? And when the packets arriving at the receiver, receivers can check these flags or check these bits and then inform the source of the data, the sources of the packets. Okay. Now, in Internet, okay, the TCP IP protocol suite, okay, yeah, let me explain. TCP is actually a transport layer service, okay? But sometimes we also call the transport layer the TCP layer. IP is actually a network layer protocol, and therefore sometimes we actually refer to the network layer as the IP layer. So TCP/IP here is actually referring to the Internet protocol stack because the transport layer is running TCP. The network layer is running IP. So these two are the very typical classical protocols that are running, okay, supporting the operation of the Internet. So in TCP IP or in Internet, we have these special bits and we call them the explicit congestion notification bits. So when the router inside the Internet, the queue size gets large enough or the free buffer space gets small enough, we set the ECN bits on. And therefore, the receiving end, the TCP receiver there, seeing the ECN bits on can inform the source to serve them. Now, that is how the routers in network-assisted approach detect congestion and notifying the source of the congestion. What's nice about this approach is this: the routers there observe exactly how much free space there is, okay? And dividing by the number of flows that's going through, number of connections that's going through. Hey, routers can also be more explicit, telling the receiver to inform the source. Now, set the sending rate to this size. Set your sending window size to a particular size, such that we will not be overwhelming, the router buffer space. Just like the flow control mechanism, right? Receiver there observing the receiving buffer, depending on how much is free, set the sending window size accordingly, and voila, problem solved. Receiving buffer will never be overwhelmed. Similarly, the router's receiving buffer here will never be overwhelmed. And we'll take a look at an example of an end-to-end based approach, TCP's congestion control mechanism. And TCP does it this way. The sender will increase the sending rate gradually if there are no packet losses detected. But as soon as there's a packet loss, we drop the sending rate drastically. So point number one here, packet loss is used as an indication of network congestion in TCP. Point number two, TCP TCP is actually implementing a trying, failing process to discover what is the proper sending rate. Now, by sending rate here, I'm adjusting. In TCP, it's implemented this way by changing the sending window size. You see that the sending window size is a limiting number of bytes we can send out within one round trip time. Therefore, increasing the sending window size is increasing the sending rate. Okay. All right, the exact process of doing the trying and failing is called the additive increase, multiplicative decrease, or AIMD to be short. So, AI describes the increasing process of the sending rate. So this is done by setting the window size and such that it increases one packet per round trip time. And the decreasing part is this cutting the window size to half of it, okay, after detecting a packet loss. So you see the increasing part is slow and linear. The decreasing part is drastic, multiplicative. So additive increase, multiplicative decrease. Okay. Linear increase, multiplicative decrease. So if I show the sending window here over time, we'll see when there are no losses, the window size is going to grow linearly. As soon as we hit the loss, we drop the window size drastically to half of it. So additive increase, multiplicative decrease. So each of these AIMD episodes looks like a sawtooth. And that is why people often say TCP's window size change over time shows a sawtooth behavior. One thing I want to add is this. We say we increase the window size by one packet per round trip time. But TCP sequence size is counting data by bytes. Window size is therefore also counting the maximum amount of data we could send out by bytes. So what do we mean by increasing the window size by one packet? That doesn't make sense. How do we implement that? Yeah, so the fact in the implementation, what's being done is to increase the window size by one maximum segment size. Okay, so MSS here, if it's configured to be 1460 bytes, then the window size is incremented by 1460 if there's no loss detected within a round. And this is actually related to the second point I want to stress. Yeah, you see here, the full name of the sending window is no longer WND. Right? It's actually called the congestion window size, CWND. Because the sending window size is dynamic in TCP, and it's actually controlled by the congestion control mechanism. That's why the window is now referred to as the congestion window. And this is TCP's process of trying to probe and discover the available bandwidth. Now let's bring up the diagram we used to explain TCP. Now it's counting bytes. Now each of these is what? A byte. If we'll be generating a new packet, then we'll be using the byte stream number here as the sequence number of the new packet. Right? So what you're seeing here is I'm updating the diagram such that this term here is no longer WND, the sending window size. We are now calling it the congestion window size, okay, because this here, okay, cwnd is dynamic. It can be large or small. It's no longer a fixed size. And how large it is depends on how the network is smooth. How small it is depends on how bad the network is congested. And the quantity cwnd here limits the number of bytes there can be between the last byte sent to the last byte act. Last byte act. So green here are counting the bytes that have been sent and have been act. So the last byte act is the last screen. Yellow here are the packets sent or the bytes sent but not yet act. So last byte sent is here, the last yellow. Okay. So last yellow, okay, subtracting the number of the last green. That means the number of yellows. Okay. So cwnd here limits the number of yellow bytes there can be at best. Last, yeah. So we say TCP's congestion control is done by controlling the sending rate or changing the sending rate to discover what is the right one. Okay. We already mentioned earlier that is actually implemented by changing the window size, changing the congestion window size, because the sending rate is essentially the congestion window size divided by RTT, because within a round trip time we can only send these many bytes, Something that's a little bit unusual in TCP's process of discovering the proper sending rate is this. There's an initialization phase, and the mechanism is called the slow start. Okay. What it does there is, when TCP is just starting, a connection is just starting, the initial window size is set to 1 MSS. And the increasing pace is no longer AIMD, it's actually what? Doubling the window size per round trip time. AIMD is what? Increasing the window size by 1 MSS per round trip time. Wow, so that's actually quite aggressive, isn't it? You are correct, because the window size in slow start, in the initialization phase, is going to increase exponentially. Because every round trip time, you double the size. Every round trip time, you double the size. As opposed to in AIMD, every round trip time, you increase by 1 segment size. Every round trip time, you increase 1 segment size. Right, so yeah, the initial rate, very, very small, 1. So the slow start is actually referring to the initial window size being the lowest possible. But the increasing rate is actually exponentially fast. Okay, so this is actually the part of design in TCP's congestion control that can confuse you a little bit. It's slow start, but it's actually increasing really, really fast, right? So the intuition says this is fast start, in fact. Yes, you are correct, but the slow here actually meant the window size, the initial value, is a very low value. Okay. The last point I want to make is this. Okay. Doubling window size per round trip time, in the implementation is actually done this way. Okay. Window size is incremented by 1 after receiving an ACK. Okay, so look at the illustration I have on the right. A is the sender, B is the receiver. A originally in slow start having a cwnd of 1 MSS. That data packet will go, receiver here will send an ACK back. Host A here being the sender, receiving an ACK will do what? cwnd ++, and the increment is 1 MSS. As a result, it was originally 1, now 2. Therefore, sender here can send 2 segments in MSS. So these will go and generate 2 ACKs coming back. Sender here receiving 2 ACKs will be calling this line twice, therefore 2 will become 4. Similarly, 4 ACKs comes back here, and this will be called 4 times, therefore the window size becomes 8. And the next round, 16. You see an exponential increase here, right? By a factor of 2, isn't it? So overall, TCP's process of discovering the proper sending rate is more like this. This is a TCP connection. And this is the beginning of it, and this is the end of it. So there's this initialization phase where we run the slow start mechanism. Okay, and the behavior of the window size is AIMD. And then in the steady phase, we run this congestion avoidance mechanism. The behavior of the window size is AIMD.